Every second, trillions of invisible particles so small and ghostly they slip through matter like it isn't even there, are streaming straight through your body right now. You can't feel them, you can't see them, but they're there, passing effortlessly through your skin, your bones, even the ground beneath your feet. These are neutrinos, the universe's most elusive cosmic travelers, and they hold secrets that could rewrite our understanding of reality itself. Yet here's the baffling part: despite the countless neutrinos flooding the cosmos, scientists are still asking one haunting question: where have they all gone? Picture this, a particle so tiny it barely interacts with anything, born in the fiery cores of stars, the explosive deaths of supernova, even the very first moments after the Big Bang. Neutrinos are cosmic fingerprints, carrying clues about the most violent and energetic events in the universe. But the more we study them, the more they seem to vanish before our eyes. Experiments designed to catch them come up short, as if the universe is playing a cosmic shell game with these ghostly particles. What's happening to them? Are they changing form, disappearing into hidden dimensions, or is our entire understanding of physics missing a crucial piece of the puzzle? This isn't just a mystery for scientists in lab coats, it's a story that touches everything from the fate of stars to the fundamental laws governing reality. If we can solve the case of the missing neutrinos, we might unlock answers to some of the biggest questions in physics. What is the universe made of? How do particles gain mass, and what hidden forces are shaping the cosmos in ways we can't yet see? In this video, we'll dive into the experiments hunting these phantom particles, the mind-bending theories trying to explain their strange behavior, and why cracking this cosmic code could change everything. Strap in, we're about to chase shadows across the universe. To understand why neutrinos are so baffling, we need to start with what makes them utterly unique in the particle zoo. Unlike electrons or protons, neutrinos carry no electric charge, meaning they don't respond to electromagnetic forces, the same forces that let you stick a magnet to your fridge or feel the warmth of sunlight. They're also unimaginably light, with masses so tiny that for decades, scientists debated whether they even had mass at all. A single neutrino is at least 10 million times lighter than an electron, making it the featherweight champion of the subatomic world. But here's the real kicker: neutrinos barely interact with matter. They're so indifferent to other particles that they can sail through an entire planet, or even a star, without a single collision. To a neutrino, Earth might as well be a ghost. This ghostly nature is why detecting them is like trying to catch smoke with your bare hands. Imagine standing in a hurricane with a butterfly net. That's roughly the scale of the challenge physicists face. Yet neutrinos aren't rare. In fact, they're one of the most abundant particles in existence. The Sun alone blasts out 65 billion neutrinos every second through every square centimeter of Earth. Supernova, those catastrophic stellar explosions, release even more in a single burst than our Sun will produce in its entire lifetime. Even bananas emit neutrinos thanks to the natural radioactivity of potassium in them. So if they're everywhere, why are they so hard to pin down? The answer lies in their origins and their journey. Neutrinos are born in some of the most extreme environments in the universe: the nuclear furnaces of stars, the crushing depths of collapsing supernova, and the violent particle showers created when cosmic rays strike Earth's atmosphere. Each of these events produces a different flavor of neutrino, electron, muon, or tau. And here's where things get even stranger. Neutrinos don't stay in one flavor. They oscillate, morphing from one type to another as they travel. This chameleon-like behavior, confirmed only in the late 20th century, was the first clue that something fundamental was missing from our understanding. But the real shock came when scientists tallied up the numbers. When detectors measured neutrinos from the sun, they found only a third of what theoretical models predicted. Where were the rest? Either our models of how stars work were catastrophically wrong, or neutrinos were pulling a disappearing act. This discrepancy, known as the solar neutrino problem, haunted physicists for decades. It wasn't until we realized neutrinos could change identities mid-flight that the pieces began to fit. The missing neutrinos weren't gone. They'd simply switched disguises, slipping past our detectors unnoticed. Yet even this revelation didn't solve everything. Neutrinos continue to defy expectations. Some experiments detect fewer neutrinos than they should at certain energies. Others hint that neutrinos might be their own antiparticles, a property that could explain why the universe is made of matter rather than antimatter. And then there's the wildest idea of all, that some neutrinos might be darting into hidden dimensions beyond our perception. Every answer we uncover seems to open 3 new questions. The story of neutrino discovery is just as dramatic as the particles themselves. It begins not with a eureka moment, but with a desperate attempt to save one of physics' most sacred laws, the conservation of energy. In the 1930s, scientists studying radioactive decay noticed energy seemed to vanish into thin air during the process. Rather than abandoning the law, Wolfgang Pauli proposed a radical solution, an invisible, nearly undetectable particle carrying away the missing energy. He famously joked that he'd done something unforgivable, theorizing a particle nobody could ever hope to see. But see it we did. 26 years later, in a Herculean feat of ingenuity, physicists built a detector deep underground, shielded from cosmic interference, and filled it with a tank of dry cleaning fluid. Why? Because when a neutrino, against all odds, did interact with a chlorine atom in that fluid, it would transform into a radioactive argon atom, leaving a trace we could measure. And in 1968, after painstakingly sifting through mountains of data, they found it, the first direct evidence of Pauli's ghost particle. It was a triumph of human persistence, proving that even the universe's shyest inhabitants can't hide forever. The hunt for neutrinos took a revolutionary turn in the mid-20th century, when 2 physicists decided to chase the impossible. Clyde Cowan and Frederick Rionese weren't content with just theorizing about these ghostly particles. They wanted to catch one in the act. Their groundbreaking experiment in 1956 didn't just confirm the existence of neutrinos, it turned particle physics upside down. Working near a nuclear reactor, a neutrino factory, in essence, they set up a detector filled with water and cadmium chloride, hoping to spot the telltale flash of light produced when a neutrino collided with a proton. It was like trying to hear a whisper in a thunderstorm, but after months of painstaking analysis, the signal emerged, as undeniable proof that Pauli's impossible particle was real. Yet this triumph came with a twist. Even as Cowan and Rionese celebrated their Nobel Prize-worthy discovery, a new puzzle emerged. Neutrinos weren't just hard to detect, they were vanishing en masse. When scientists compared the number of neutrinos they expected from the sun or nuclear reactors to what their experiments actually measured, the math never added up. It was as if someone had turned off a cosmic faucet halfway. Where were the missing neutrinos? Some joked that the universe was gaslighting physicists, but the implications were dead serious. If our detectors were right, then either the sun wasn't working the way we thought, or neutrinos were pulling off the greatest magic trick in physics. This vanishing act led to one of the most startling revelations in modern science. Neutrinos aren't just passive spectators in the universe, they're shape-shifters. Researchers realized these particles could oscillate between three different flavors: electron, muon, and tau, mid-flight. A neutrino born in the sun's core might start its journey as an electron neutrino, only to morph into a muon neutrino by the time it reaches Earth. Since early detectors could only spot one flavor, they were effectively blind to the others, making it seem like neutrinos were disappearing. It was like counting cars on a highway but only tallying the red ones. You'd swear traffic was lighter than it really was. But here's where the story gets even stranger. Neutrino oscillation shouldn't be possible unless these particles have mass, a notion that contradicted the long-held standard model of physics, which assumed neutrinos were massless. This tiny wobble in their identity forced scientists to rewrite the rules. Suddenly, the lightest particles in existence were also the most rule-breaking, hinting at gaps in our understanding of the universe's fundamental blueprint. And the deeper we looked, the weirder it got. Some experiments began detecting anomalies, neutrinos that oscillated faster or slower than predicted, or hints of a mysterious fourth flavor, the sterile neutrino, that might only interact with gravity. What started as a quest to balance an equation has become a full-blown cosmic detective story. Every time we think we've pinned neutrinos down, they slip through our fingers again, leaving behind clues that point to something bigger. Are they messengers from hidden dimensions, keys to why the universe favors matter over antimatter, or something even more extraordinary? One thing's certain: these phantom particles aren't done surprising us. For decades, the sun became ground zero for one of physics' most frustrating mysteries. Every calculation told us how many neutrinos should be streaming from its core, where nuclear fusion transforms hydrogen into helium, releasing unimaginable energy. The math was solid, backed by everything we knew about stellar physics. Yet when detectors here on Earth counted the incoming solar neutrinos, the numbers were off by a staggering margin. 2/3 of them were simply missing. This wasn't just a small error. It was a gap so large it threatened to unravel our understanding of how stars work. At first, scientists scrambled to double-check their instruments. Maybe the detectors were flawed, or perhaps the calculations about the sun's energy output were wrong. But the more they verified, the clearer it became. The problem wasn't with the equipment or the models. The neutrinos themselves were behaving in ways nobody anticipated. Imagine setting up a rain gauge to measure a storm, only for it to catch just a few drops while everything around you stays dry. That's how baffling this discrepancy felt. The breakthrough came when physicists considered a radical idea. What if the missing neutrinos weren't missing at all? What if they'd simply changed into something our detectors couldn't see? This hunch led to the discovery of neutrino oscillation, a quantum quirk where neutrinos switch between their three flavors as they travel. An electron neutrino leaving the sun might arrive at Earth as a muon or tau neutrino, invisible to detectors tuned only for the original flavor. It was like a magician's sleight of hand. The particles were there all along, just disguised, but solving one mystery only deepened another. For neutrinos to oscillate, they had to have mass, a property the standard model of particle physics insisted they couldn't possess. This tiny detail sent shockwaves through the scientific community. If neutrinos had even a whisper of mass, it meant our most fundamental theories were incomplete. Suddenly, the smallest particles in existence became the biggest troublemakers, forcing physicists to rethink the rules of the universe. The implications stretch far beyond the sun. Neutrino oscillations could hold clues to why the cosmos is made of matter instead of antimatter, a bias that allowed galaxies, stars, and ultimately us to exist. Some theories even suggest these shape-shifting particles might be cosmic messengers, hinting at hidden dimensions or new forces we've yet to discover. What started as a counting error in a solar experiment has become a window into the universe's deepest secrets, proof that sometimes the smallest things can cast the longest shadows. The discovery that neutrinos could change identities like cosmic undercover agents didn't just solve the mystery of their disappearance, it thrust us into the bizarre world of quantum mechanics, where the rules defy common sense. Imagine flipping a coin and watching it morph into a die mid-air, then into a marble before landing. That's the level of strangeness we're dealing with. Neutrinos accomplish this trick through a phenomenon called quantum superposition, where a particle exists as a blend of all possible states until it's measured. For neutrinos, that means an electron neutrino isn't just an electron neutrino. It's simultaneously a mix of all three flavors, with the odds of collapsing into any one of them shifting as it travels. This shape-shifting act hinges on a delicate quantum dance between mass and flavor. Here's the twist. The three neutrino flavors we detect don't align perfectly with their three mass states, quantum versions of neutrinos with distinct, if infinitesimal, weights. As a neutrino zooms through space, these mass states evolve at slightly different rates due to their differing masses, altering the flavor mixture like waves interfering in a pond. By the time the neutrino reaches a detector, its original identity might be completely scrambled. It's not magic, it's math written in the language of quantum probabilities. The proof arrived in two landmark experiments that turned neutrino physics upside down. In Japan, the Super-Kamiokande detector, a colossal tank buried deep underground, filled with 50,000 tons of ultra-pure water, caught muon neutrinos produced in Earth's atmosphere, changing flavors as they passed through the planet. Meanwhile, Canada's Sudbury Neutrino Observatory cracked the solar neutrino puzzle by using heavy water to capture all three flavors, proving the sun wasn't underproducing neutrinos. They'd just been in disguise. These triumphs earned their teams Nobel Prizes, but they also exposed how little we truly understood. Why does this matter beyond filling textbooks? Because neutrino oscillations shouldn't happen if these particles are massless, as the standard model once assumed. Their tiny masses imply new physics lurking beyond our current theories, perhaps extra dimensions, unknown particles, or forces that could rewrite the cosmic rulebook. Even stranger, neutrinos might hold the key to one of the universe's greatest imbalances: why matter dominates over antimatter. If neutrinos and their antimatter counterparts oscillate differently, they could have tipped the scales in the early universe, allowing galaxies like ours to exist. Yet every answer breeds new questions. Why do neutrinos have such absurdly small masses compared to other particles? Could there be a fourth, even more elusive, sterile neutrino, detectable only by its gravitational shadow? The more we learn, the clearer it becomes. Neutrinos aren't just passive bits of the cosmos. They're active players in a quantum game we're only beginning to decipher, one where the stakes are nothing less than understanding the universe itself. To grasp why neutrinos perform their quantum vanishing act, we need to step into a world where particles exist as shimmering probabilities rather than solid objects. At the heart of their oscillation lies a peculiar marriage between Einstein's relativity and the fuzzy logic of quantum mechanics. Picture a neutrino not as a tiny billiard ball, but as a packet of waves, each representing one of its possible mass states. These waves travel at slightly different speeds because, unlike the standard model's prediction, neutrinos do have minuscule masses. The heavier the mass state, the slower its wave moves through space. Over astronomical distances, these waves fall out of sync, creating an interference pattern that shifts the odds of the neutrino, collapsing into one flavor or another when measured. The math behind this is both elegant and mind-bending. The probability of a neutrino changing flavors depends on three factors: the energy of the neutrino, the distance it travels, and the differences between the squares of their masses. Yes, squares, because in quantum physics, probabilities hinge on amplitude squared. This is why oscillation patterns vary wildly between neutrinos born in the sun's core, low energy, long journey, versus those produced in particle accelerators, high energy, short distance. It's also why certain experiments, like those measuring neutrinos shot through Earth's crust, can detect the subtle beats in this quantum rhythm as flavors flicker like a cosmic strobe light. But here's the real kicker: neutrino oscillation shouldn't exist if these particles were truly massless, as the original Standard Model insisted. Their tiny masses, spanning just millionths of an electron-volt, are like finding a single grain of sand in a desert the size of the solar system. Yet that infinitesimal weight cracks open the door to profound questions. Why do neutrinos have mass when the model's equations assumed they wouldn't? Could their mass arise from an entirely different mechanism than other particles, perhaps tied to undiscovered forces or particles? Some theories, like the seesaw mechanism, suggest heavy, right-handed neutrinos might exist, pulling down the masses of the ones we observe to almost nothing. Others speculate these particles might be Majorana fermions, entities that are their own antimatter, twins, a property that could explain why the universe didn't annihilate itself in a burst of pure energy after the Big Bang. This isn't just academic curiosity. Neutrino masses might hold the key to one of cosmology's biggest puzzles. Why does anything exist at all? If neutrinos and antineutrinos oscillate differently, a phenomenon called CP violation, they could have tipped the early universe's matter-antimatter balance by a hair, allowing galaxies and life to emerge. Experiments like Dune and Super-Kamiokande and are hunting for this asymmetry, aiming to catch neutrinos in the act of rewriting cosmic history. Meanwhile, anomalies in reactor neutrino data keep teasing the possibility of a fourth, sterile flavor, a ghost even more elusive than the ones we know, interacting only via gravity. If real, it could signal particles from hidden dimensions or dark matter's shadowy kin. What began as a quirk of quantum mechanics has become a seismic shift in physics. Neutrino oscillation didn't just solve a solar accounting error. It revealed that the universe's instruction manual has pages we've yet to read. And with every flicker of these quantum chameleons, they whisper a tantalizing question: what else are we missing? The Standard Model of particle physics is often called the most successful scientific theory ever devised, a masterpiece of equations that predicted the existence of particles decades before we found them. But neutrinos tore a hole in that flawless tapestry. For years, the model insisted these particles should be massless, like photons zipping through space at the speed of light. Then came the undeniable proof of neutrino oscillation, revealing they had mass after all, tiny, yes, but enough to send shockwaves through the foundations of physics. It was as if we'd spent centuries perfecting a map of the world, only to suddenly discover an entire continent we'd missed. This isn't just a minor tweak to the rules. Neutrino masses imply something profound. The Standard Model is incomplete. Hidden beneath its polished surface could lie entirely new particles, forces, or even dimensions, ingredients we haven't yet imagined. Some theorists speculate neutrinos might be bridges to gravity, the one fundamental force that stubbornly resists being shoehorned into quantum theory. Others wonder if they're entangled with dark matter, the invisible scaffolding holding galaxies together. After all, if neutrinos can evade detection so effortlessly, who's to say more elusive particles aren't out there, shaping the cosmos in ways we can't yet see? Perhaps the most tantalizing clue neutrinos offer is their potential role in the universe's greatest imbalance: why matter dominates over antimatter. According to the Big Bang, equal amounts of both should have annihilated each other, leaving behind a sea of pure energy. Yet here we are in a universe brimming with stars, planets, and life. Neutrinos might hold the answer if they violate a symmetry called CP violation, where particles and their antimatter counterparts behave differently. They could have tilted the scales in matter's favor during the universe's first fiery moments. Experiments like Japan's T2K and the upcoming Deep Underground Neutrino experiment are racing to catch this asymmetry in action, hunting for neutrinos that flicker between flavors differently than their antimatter twins. The hunt for these phantom particles has spawned some of the most audacious experiments in science. Take IceCube, a detector buried in the Antarctic ice, using a cubic kilometer of frozen water to catch neutrinos from distant supernova or colliding black holes. Or the planned Dune project, which will shoot neutrinos 800 miles through Earth's crust to study their oscillations with unprecedented precision. These aren't just tools, they're time machines, letting us peer back to the universe's birth and decode messages from its most violent events. Yet for every mystery neutrinos solve, they unveil two more. Why are their masses so inexplicably small compared to other particles? Could sterile neutrinos, hypothetical cousins that ignore every force except gravity, be lurking in the shadows? Each question pulls us deeper into the unknown, reminding us that the universe's quietest particles might be its loudest teachers. The standard model was never the final word, it was a starting point, and neutrinos are leading us toward the next revolution. Buried beneath the Antarctic ice, where temperatures plunge to -50 degrees and sunlight never reaches, lies one of the most unlikely scientific instruments ever built, IceCube. This colossal observatory isn't made of gleaming metal or glass, but of a cubic kilometer of pristine ice, threaded with thousands of sensors waiting for the faintest flash of light. Why? Because when a high-energy neutrino, born in the heart of a distant galaxy or a cataclysmic supernova, finally collides with an atom in this frozen expanse, it creates a fleeting burst of blue radiation known as Cherenkov light. IceCube's job is to catch these cosmic whispers, turning the Antarctic into a giant neutrino telescope. But IceCube isn't alone in this hunt. Half a world away, in the depths of an old gold mine in South Dakota, scientists are preparing for the deep underground neutrino experiment Dune, a project so ambitious it could redefine particle physics. Dune detectors, filled with liquid argon cooled to nearly 200 degrees below zero, will track neutrinos fired 800 miles through Earth's crust from a particle accelerator in Illinois. The goal: to capture these particles mid-oscillation, studying their shape-shifting tricks with precision never before possible. Why go to such extremes? The answer lies in the delicate nature of the quarry. Neutrinos are so indifferent to matter that even air molecules or stray cosmic rays can drown out their signals. By burying detectors deep underground, or in IceCube's case, deep under ice, scientists create a natural shield. The rock and ice absorb interfering particles, leaving only neutrinos, which pass effortlessly through miles of Earth to reach the sensors. It's like trying to hear a single violin in a thunderstorm by building a silent chamber a mile below the surface. The payoff is extraordinary. IceCube has already spotted neutrinos with energies millions of times greater than those produced in particle colliders, tracing them back to black holes and violent galactic jets. Dune, meanwhile, could uncover whether neutrinos and antineutrinos oscillate differently, a clue to why the universe didn't vanish in a puff of antimatter annihilation. These observatories aren't just machines, they're time capsules, decoding messages from the universe's most explosive events and its earliest moments. Yet the deeper we dig, the stranger the story becomes. Recent data hints at anomalies, neutrinos behaving in ways the models can't explain. Could there be a fourth flavor, a sterile neutrino that interacts only via gravity? Or are we glimpsing shadows of physics beyond the standard model? Every new detector brings us closer to answers and deeper into the mystery. To catch the universe's most elusive particles, scientists have to think like spies, building their detectors in places so isolated they might as well be on another planet. Take Italy's Gran Sasso National Laboratory, nestled under a mountain of rock so thick it blocks out nearly all cosmic rays. Or Japan's Super-Kamiokande, a tank of 50,000 tons of water buried a kilometer underground, where sensors wait in darkness for the faintest flicker of a neutrino's passing. These aren't just labs, they're fortresses designed to shield against the constant storm of radiation raining down from space. Cosmic rays, high-energy particles from distant supernovae, and black holes bombard Earth's surface at a rate of thousands per square meter every second. To a neutrino detector, this is like trying to hear a whisper in a hurricane. But by going deep underground, scientists use the planet itself as a filter. A mile of rock stops virtually all cosmic rays, while neutrinos slip through effortlessly. It's the ultimate game of hide and seek, with Earth's crust as the playing field. The engineering behind these detectors is as breathtaking as the science they enable. Consider the tanks of ultra-pure water in Super-Kamiokande, and so clean that even a single stray atom could skew results. Or Dune cryogenic argon chambers, kept at temperatures colder than deep space to preserve the fleeting trails left by neutrino collisions. These aren't just experiments, they're monuments to human ingenuity, built to capture particles that treat solid matter like empty air. Yet neutrinos aren't just laboratory puzzles, they're cosmic telegrams carrying news from the universe's most violent events. When a star explodes as a supernova, 99% of its energy escapes as neutrinos, racing ahead of the light blast. In 1987, detectors on Earth caught neutrinos from a supernova in the Large Magellanic Cloud hours before telescopes saw the flash proof that these particles are the fastest, most efficient messengers in the cosmos. Some neutrinos carry even wilder pedigrees. Astrophysicists have traced ultra-high-energy neutrinos back to Blazar's supermassive black holes firing jets of plasma straight at Earth. Others might hail from the wreckage of colliding neutron stars or the fiery hearts of active galaxies. Each one is a fingerprint of the extreme physics that shaped it, a clue etched in quantum code. The deeper we dig, the more we realize neutrinos aren't just passing through our detectors, they're passing through history itself. Some of the neutrinos hitting Earth today were born in the first seconds after the Big Bang, frozen relics from the universe's fiery infancy. Others might be streaming from events so distant their light hasn't reached us yet. In this way, neutrino astronomy isn't just about studying space, it's about studying time, peeling back layers of cosmic history one ghostly particle at a time. What makes these particles such extraordinary messengers is their refusal to be sidetracked. Unlike light, which can be absorbed or scattered by dust and gas, neutrinos travel in straight lines from their sources, unbothered by magnetic fields or interstellar debris. A neutrino from a distant quasar arrives at Earth with its story intact, pristine after billions of years. It's as if the universe handed us a telescope with perfect vision, if only we could learn to read its signals. That's the real magic of these underground cathedrals of science. They're not just shielding detectors from noise, they're shielding humanity from ignorance, giving us front-row seats to the universe's grandest spectacles. And with every neutrino caught, we're one step closer to decoding the messages they've carried across space and time. The Sun may be our closest neutrino factory, but it's far from the most dramatic. Deep within its core, where temperatures soar to 15 million degrees, nuclear fusion transforms protons into helium, releasing not just sunlight but a flood of low-energy electron neutrinos, 65 billion, passing through your thumbnail every second. Yet these solar neutrinos are just the faint hum of a cosmic orchestra. For real fireworks, we must look to the universe's most violent events. Take a supernova, the explosive death of a massive star. When its core collapses under its own gravity, it doesn't just implode into a neutron star or black hole. It becomes a neutrino supernova. For a few seconds, the dying star emits more neutrinos than all the stars in the observable universe combined. These aren't the gentle solar neutrinos we're used to, their high-energy messengers, packing details about the star's final moments. In 1987, detectors on Earth caught 24 neutrinos from SN 1987A, a supernova in the Large Magellanic Cloud. That handful of particles confirmed theories about how stars die. The neutrino pulse arrived hours before the visible light, proving the collapse's shockwave takes time to reach the surface. Those fleeting detections were like intercepting a cosmic SOS, sent in real time from a cataclysm 168,000 light-years away. But supernovae aren't the only extreme neutrino producers. Active galactic nuclei, supermassive black holes devouring matter at the centers of galaxies, launch jets of plasma, so energetic they create neutrinos with 1 billion times more energy than those from our Sun. In 2018, IceCube traced one such neutrino back to a blazar 4 billion light-years away, marking the first time we'd pinpointed a high-energy neutrino to its source. These particles are cosmic bullets fired across the universe by forces we're only beginning to understand. What makes neutrinos so valuable isn't just their abundance, it's what they carry. Unlike light, which can be scattered or absorbed, neutrinos fly straight from their birthplaces, untouched by magnetic fields or interstellar gas. Their energy spectra, the distribution of their speeds and flavors, act like barcodes, revealing conditions inside stars and explosions. Solar neutrinos, for example, confirm that the Sun's energy comes from fusion, not chemical burning. Supernova neutrinos encode details about the collapsing core's density and temperature. Even the diffuse neutrino background, a whisper left over from the Big Bang, could tell us about the universe's first second. Now, imagine harnessing these particles as tools to probe the unseen. Neutrinos from distant active galaxies might unveil hidden black holes shrouded in dust. Those passing through Earth could expose mineral deposits or even monitor nuclear reactors for illicit activity. Some theorists speculate that ultra-high-energy neutrinos might betray the presence of cosmic strings, hypothetical defects in spacetime left over from the universe's birth. Yet the grandest possibility lies in dark matter. If sterile neutrinos exist, they could be the very fabric of this invisible cosmic scaffolding, interacting only through gravity. Catching one would solve two mysteries at once: the nature of neutrinos and the identity of the universe's missing mass. Every neutrino we detect is more than a particle. It's a cipher waiting to be cracked. And as our detectors grow more sophisticated, these ghostly messengers may finally reveal the universe's best-kept secrets. Among the countless mysteries woven into the fabric of the cosmos, two stand out as especially perplexing: the nature of dark matter and the puzzling dominance of matter over antimatter. Remarkably, neutrinos, those ghostly particles we've struggled to detect, might hold clues to both. One of the most intriguing theories suggests the existence of a hypothetical fourth flavor of neutrino, dubbed the sterile neutrino, which could be a hidden component of dark matter itself. Unlike the three known neutrino flavors, sterile neutrinos would interact only through gravity, making them nearly impossible to spot with conventional detectors. If they exist, they could be lurking all around us, invisible yet shaping the very structure of galaxies. The idea isn't as far-fetched as it sounds. Ordinary neutrinos already stretch the limits of physics with their vanishingly small masses and elusive behavior. If sterile neutrinos are real, they could explain why dark matter seems to outnumber visible matter 5 to 1. Some models propose these particles were forged in the early universe, left over from a time when conditions were so extreme that even neutrinos could have heavier, more exotic siblings. Experiments like Mini Bueni at Fermilab have spent years hunting for anomalies in neutrino behavior that might hint at these hidden particles' tiny discrepancies in oscillation patterns or unexpected energy distributions that could betray the presence of something new. But the hunt is fraught with challenges. Sterile neutrinos, if they exist, would be even more reluctant to interact than their known counterparts. Detecting them would require instruments of unprecedented sensitivity, capable of spotting the faintest gravitational whispers. Some researchers are turning to the cosmos itself for answers, scouring data from telescope surveys for distortions in the light of distant galaxies' subtle bends that might reveal sterile neutrinos warping spacetime as they pass. Others are refining underground detectors, hoping to catch a rare, telltale flicker of interaction. Meanwhile, neutrinos might hold another cosmic secret: why the universe didn't vanish in a burst of pure energy after the Big Bang. According to physics, matter and antimatter should have annihilated each other in equal measure, leaving nothing behind. Yet here we are in a universe made almost entirely of matter. Neutrinos, with their ability to oscillate between flavors, could be the key. If they violate a symmetry known as CP violation, where particles and antiparticles behave differently, they might have tipped the scales ever so slightly in matter's favor during the universe's infancy. Experiments like Japan's T2K and the upcoming Deep Underground Neutrino experiment are searching for this asymmetry, watching closely to see if neutrinos and antineutrinos oscillate at different rates. What makes these questions so compelling is their sheer scope. Solving the mystery of sterile neutrinos wouldn't just fill in a gap in the standard model. It could rewrite our understanding of dark matter, galaxy formation, and the fate of the cosmos itself. Similarly, uncovering neutrinos' role in matter's dominance would reveal how the universe avoided self-destruction, making life and galaxies possible. For now, the answers remain just out of reach, hidden in the quantum flickers of particles that barely interact with reality. But if history has taught us anything, it's that neutrinos love to surprise us. Every time we think we've pinned them down, they reveal another layer of mystery, and with it, the promise of discoveries that could reshape physics as we know it. Every atom in your body, every star in the sky, every planet in the cosmos, they all exist because of a tiny cosmic oversight, a slight imperfection in the universe's original blueprint. According to the laws of physics, the Big Bang should have created equal amounts of matter and antimatter, particles and their mirror opposites. When matter and antimatter meet, they annihilate in a flash of pure energy. So why didn't everything cancel out, leaving behind nothing but empty space? The answer might lie with neutrinos and their quantum sleight of hand. Here's the puzzle. For every billion matter-antimatter pairs born in the early universe, just one extra matter particle survived. That razor-thin margin, 1 in a billion, is all that separates us from oblivion. Scientists call this imbalance CP violation, where particles and antiparticles don't behave quite symmetrically. And neutrinos, with their chameleon-like oscillations, might be the culprits behind this cosmic heist. Imagine a scale balancing matter and antimatter, perfectly even until neutrinos, like invisible weights, nudged it ever so slightly in matter's favor. The leading theory, leptogenesis, suggests that ultra-heavy neutrinos in the early universe decayed unevenly, producing more matter than antimatter. these particles would have been far more massive than the neutrinos we know today, vanishing almost instantly but leaving behind a legacy, a universe tilted toward existence. It's a staggering thought. The very particles that slip through our detectors unseen might have orchestrated the conditions for galaxies, planets, and life itself. But before we drift too far into the cosmos, let's ground this in something closer to home. Neutrinos don't just shape the universe's grand design, they leave fingerprints on Earth, too. Deep inside our planet, radioactive decays in the mantle produce neutrinos, particles that carry heat from Earth's core. By catching these ghostly messengers, scientists can map the planet's inner workings, tracing the slow churn of molten rock that drives volcanoes and tectonic shifts. It's like taking an X-ray of the Earth, using particles that traveled thousands of miles through solid rock to reach our detectors. Even more surreal, some of the neutrinos passing through you right now are relics of the early universe, unchanged since the first second after the Big Bang. Others were born in the sun's core 8 minutes ago or in a distant supernova millions of years back. They're not just particles, they're time travelers carrying stories from across the ages. And if we're right about their role in the matter-antimatter imbalance, they might be the reason those stories have an audience at all. The search for proof is underway in labs around the world. Experiments like Dune and Super-Kamiokande are tuning their detectors to spot the faintest hints of CP violation in neutrino oscillations. If they find it, the implications would be monumental. Neutrinos wouldn't just be bystanders in cosmic history, they'd be the architects of everything we see. For now, the data teases us with possibilities, a cosmic whisper just barely out of earshot. But if there's one thing neutrinos have taught us, it's that the universe's quietest particles often have the loudest things to say. Deep beneath our feet, in the swirling molten rock of Earth's mantle, a silent process has been unfolding for billions of years. Radioactive elements like uranium and thorium decay, releasing not just heat but ghostly messengers called neutrinos. These particles, born from the very atoms that keep our planet's core churning, are the only direct signals we have from Earth's radioactive heart. While most neutrinos come from the cosmos, neutrinos tell a homegrown story, carrying secrets about the forces that shape volcanoes, tectonic plates, and even the magnetic field shielding us from solar storms. Detecting these faint whispers requires instruments as precise as they are rugged. Japan's Camland detector, nestled in a mine a kilometer underground, was the first to spot neutrinos in 2005. By filling a giant balloon with liquid scintillator, a cocktail of chemicals that lights up when a neutrino interacts, scientists could separate these earthly particles from the cosmic neutrino background. The data revealed something startling. About half of Earth's internal heat comes from radioactive decay, while the rest is leftover energy from the planet's violent formation 4.5 billion years ago. It's like taking a biopsy of Earth's core without drilling an inch. But neutrinos do more than just tally heat, they map the invisible. Traditional geology relies on seismic waves to infer Earth's structure, like deducing the shape of a room by listening to echoes. Neutrinos, by contrast, offer a direct sample of the mantle's composition, revealing where radioactive elements are concentrated and how they migrate over eons. This could solve long-standing mysteries, like why some regions have more volcanic activity than others, or whether Earth's heat engine is slowly winding down. The implications stretch beyond our planet. If we can refine neutrino detection, we might one day use them to locate underground deposits of uranium or thorium, resources critical for clean energy. Even wilder, some scientists propose that neutrino detectors could monitor nuclear reactors globally, acting as tamper-proof sentinels against clandestine weapons programs. A particle that ignores mountains and oceans might become an unlikely tool for diplomacy. Yet neutrinos are just one thread in neutrino science's tapestry. From Earth's depths to the edges of the observable universe, these particles connect scales we once thought unrelated. The same physics that explains why our planet stays warm might also reveal why the universe didn't vanish into nothingness after the Big Bang. As detectors grow more sensitive, we're not just studying neutrinos, we're learning to read the universe's hidden language, written in the faintest ink imaginable. At first glance, the idea that neutrinos, the universe's lightest, most ghostly particles, could shape the fate of galaxies seems absurd. After all, a single neutrino is so insubstantial that trillions pass through you every second without a trace. But when you scale up those whisper weights to the cosmic level, their collective influence might be rewriting the story of the universe itself. One of the most tantalizing possibilities is that neutrinos could be entangled with dark energy, the mysterious force accelerating the expansion of space. If neutrinos interact with this unseen driver of cosmic inflation, even weakly, their oscillations might leave fingerprints on the large-scale structure of the cosmos. Galaxies don't form randomly. They cluster along invisible filaments of dark matter, a scaffold built by gravity over billions of years. But neutrinos, with their tiny but non-zero masses, could be subtly warping this blueprint. Because they move at near light speeds, they resist being trapped by gravity's pull, smearing out the density of matter just enough to alter how galaxies assemble. Supercomputer simulations suggest this effect might explain why some galaxy clusters appear slightly less clumped than dark matter models predict. It's as if the universe's lightest particles are scattering cosmic breadcrumbs, quietly guiding where stars will blaze to life. Then there's the bigger puzzle, the universe's accelerating expansion. Dark energy, making up 68% of the cosmos, is the dominant force behind this runaway growth. But what if neutrinos hold clues to its nature? Some theories propose that as the universe expands and cools, neutrinos could undergo phase transitions, shifting their properties in ways that release or absorb energy, tweaking the dark energy equation. Others speculate that sterile neutrinos, if they exist, might decay into particles that fuel cosmic acceleration. These ideas are still speculative, but they hint at a profound connection between the smallest particles and the largest structures in existence. Studying such elusive effects requires more than just detectors. It demands cosmic archaeology. By mapping the distribution of galaxies across billions of light years, astronomers can infer how neutrinos have sculpted spacetime. The faint shadows they leave in the cosmic microwave background, the afterglow of the Big Bang, might reveal how early neutrino behavior seeded today's vast voids and superclusters. Even more remarkably, neutrino observatories like IceCube are now teaming up with gravitational wave detectors to cross-reference cosmic cataclysms. When a neutron-star collision sends ripples through spacetime, the accompanying neutrino burst could help measure how these particles interact with gravity itself. The ultimate question isn't just whether neutrinos influence cosmic evolution, it's whether they're quietly steering the universe toward a particular fate. If their masses or interactions shift over time, they might one day tip the balance between expansion and collapse. For now, every anomaly in galaxy surveys, every unexpected pattern in neutrino data is a potential clue. The universe's lightest particles may be its most subtle architects, weaving gravity's tapestry one ghostly thread at a time. Tracking neutrinos through their ghostly journeys requires a kind of scientific detective work unlike anything else in physics. Since these particles barely interact with matter, scientists can't observe them directly. Instead, they hunt for the fleeting aftermath of a neutrino's rare collision with an atom. Picture a high-energy neutrino streaking through the ice of Antarctica at nearly the speed of light. Once in a blue moon, it'll slam into an atomic nucleus, shattering it and spawning a secondary particle called a muon. This muon, now charged and eager to interact, races through the ice faster than light can travel in that medium, creating a shockwave of blue Cherenkov radiation in its wake. It's this faint, underwater glow like a cosmic bullet's sonic boom that detectors like IceCube are built to catch, but spotting the light is just the beginning. Reconstructing a neutrino's path from these scattered breadcrumbs is like solving a cosmic crime scene with only a single fingerprint. The muon's trail might stretch for kilometers, but the angle and intensity of the Cherenkov light reveal the original neutrino's energy and direction. Supercomputers then crunch the data, tracing these faint signals backward to pinpoint where in the sky the neutrino came from. Whether it's a supernova in a nearby galaxy or a black hole's jet billions of light years away. Some experiments push this indirect detection to even wilder extremes. Take ANITA, the Antarctic Impulsive Transient Antenna, a balloon-borne detector floating high above the ice. Instead of hunting for light, ANITA listens for radio waves generated when ultra-high-energy neutrinos, those with energies 1,000,000 times greater than what particle accelerators can produce, plow into the Antarctic ice sheet. These collisions create explosive showers of particles, emitting radio pulses that ANITA-sensitive antennas can pick up. It's like eavesdropping on the universe's most violent events through static. What makes these techniques so revolutionary is that they turn entire landscapes into telescopes. IceCube transforms a cubic kilometer of Antarctic ice into a neutrino observatory. ANITA uses Earth's atmosphere as a giant detector medium. Even oceans have been proposed as neutrino hunting grounds, with projects like KM3, NET deploying sensors beneath the Mediterranean to catch the faint glow of deep-sea collisions. Yet for all their ingenuity, these methods have limits. The universe's highest energy neutrinos are so rare that detectors might catch just a handful in a decade. Background noise from cosmic rays, charged particles raining down from space, can muddy the data, requiring painstaking filtering. And then there's the ultimate frustration. Neutrinos from astrophysical sources rarely come with return addresses. Unless they arrive in tandem with a gamma-ray burst or gravitational wave, tracing them back to their birthplace is like finding a needle in a cosmic haystack. These challenges aren't just technical, they're philosophical. Every time we push the boundaries of neutrino astronomy, we're forced to confront how much of the universe remains hidden from view. Neutrinos might be the ultimate cosmic messengers, but their whispers are so faint, so easily drowned out by the universe's noise, that unlocking their full potential will require detectors we haven't even dreamed of yet. The hunt isn't just about catching particles, it's about learning to listen to a universe that speaks in riddles. Even after decades of breakthroughs, neutrinos remain the ultimate cosmic enigmas. Particles so strange they've rewritten the rules of physics, yet still guard their deepest secrets. Take their masses. We know neutrinos have mass, but pinning down exactly how much is like trying to weigh a shadow. The best experiments can only place upper limits, revealing that the heaviest neutrino is at least 6 million times lighter than an electron. Why such an absurdly tiny weight compared to every other particle? Some theories suggest neutrinos might not get their mass from the Higgs field like their counterparts. Instead, they could acquire it through an entirely different mechanism, perhaps involving hypothetical heavy, right-handed neutrinos or interactions with undiscovered fields. If true, this would mean our universe has more layers of particle physics than we ever imagined. Then there's the question haunting physicists like a ghost in the data. Are neutrinos their own antiparticles? Most particles have distinct antimatter twins, electrons and positrons, protons and antiprotons. But neutrinos might break this pattern. If they're what's called Majorana particles, a neutrino and an antineutrino could be one and the same, flipping identities like a quantum coin. This wouldn't just be a curiosity. It could explain why the universe didn't annihilate itself after the Big Bang. Majorana neutrinos might have triggered a process called leptogenesis, where their decays favored matter over antimatter by a hair, just enough to leave behind the galaxies and atoms we see today. Experiments like NEXT in Spain and LEGEND in Germany are hunting for a telltale signal called neutrinoless double beta decay, a rare nuclear process that could only happen if neutrinos are their own antiparticles. Spotting it would be like finding a cosmic fingerprint, proof that these particles played a pivotal role in our existence. But the mysteries don't stop there. Why do neutrinos oscillate between flavors at all? The math behind their quantum shuffling hints at something deeper, a hidden structure in the laws of physics we haven't yet uncovered. Some models propose extra dimensions, curled up so small we'd never notice, where neutrino oscillations might be influenced by unseen forces. Others speculate about sterile neutrinos, a hypothetical fourth flavor that interacts only through gravity, making it a prime dark matter candidate. The fact that neutrino masses are so bizarrely small might even point to a cosmic accident, a cancellation between opposing effects in the early universe that left these particles nearly weightless by chance. The answers could lie in machines we're only beginning to build. Future colliders like the proposed Future Circular Collider at CERN might produce heavy neutrinos never before seen, while next-generation detectors like DUNE and Super-Kamiokande and will scrutinize oscillations with unprecedented precision. There's even talk of harnessing quantum computers to simulate neutrino behavior in ways classical machines can't. Every new experiment is a step toward unraveling these riddles, and with each discovery, we're not just learning about neutrinos. We're decoding the universe's hidden blueprint, one ghostly clue at a time. The next chapter in humanity's quest to unravel the neutrino mystery is taking shape in some of the most ambitious science projects ever conceived. In Japan, workers are excavating a cavern deep beneath Mount Aikno to house Super-Kamiokande and a next-generation neutrino detector so vast it could swallow the Statue of Liberty whole. This cylindrical behemoth, filled with 260,000 tons of ultra-pure water and lined with 40,000 light sensors, will dwarf its predecessor Super-Kamiokande, and in both size and sensitivity. Meanwhile, in southern China, the Jiangmen Underground Neutrino Observatory (JUNO) is preparing to study neutrinos from nuclear reactors with a liquid scintillator detector so precise it could spot a single candle flame from 500 miles away. These megaprojects represent a quantum leap in our ability to study neutrino oscillations, with Super-K aiming to measure CP violation with 10 times the precision of current experiments. What makes these detectors so revolutionary isn't just their scale, it's their ability to catch neutrinos in multiple ways simultaneously. Super-K will study both atmospheric neutrinos produced when cosmic rays strike Earth's atmosphere and artificial neutrino beams fired from Japan's J-Park facility 300 kilometers away. JUNO, positioned at equal distance from two nuclear power plants, will capture reactor neutrinos with unprecedented energy resolution. Together, they'll create the most detailed neutrino oscillation map ever, potentially revealing whether neutrinos and antineutrinos oscillate differently, that crucial CP violation that could explain matter's cosmic dominance. But the neutrino revolution isn't confined to pure physics. These ghostly particles are finding surprising real-world applications that sound like science fiction. In nuclear nonproliferation, neutrino detectors could monitor reactors remotely, as the particles pass unhindered through any shielding. Neutrino measurements are already helping map Earth's interior heat sources, with potential applications in predicting volcanic activity. Even more astonishing, some researchers propose using neutrino beams for communication with submarines at ocean depths where radio fails, or as a fail-safe global messaging system that couldn't be blocked by solar flares or warfare. Perhaps the wildest application lies in astronomy. When completed, projects like IceCube Gen 2, an upgraded version of the Antarctic Neutrino Telescope, could detect high-energy neutrinos from the earliest moments of the universe. These particles, unaffected by the cosmic dark ages when light couldn't travel freely, might carry untouched information from before the first stars formed. It's like discovering a cosmic time capsule buried at the dawn of time, waiting to be opened by detectors still on the drawing board. The irony is delicious. After decades struggling to detect neutrinos at all, we're now entering an era where they might become one of our most versatile tools for exploring and even navigating the universe. From unlocking the secrets of cosmic asymmetry to securing global communications, these shadowy particles are proving that sometimes the hardest things to catch turn out to be the most valuable. Neutrinos might be the universe's most reluctant participants, but their very reluctance makes them invaluable tools here on Earth. Take nuclear reactors. While they produce energy, they also generate a steady stream of antineutrinos, particles so elusive they escape containment effortlessly. This ghostly byproduct has become an unlikely watchdog for nuclear nonproliferation. By placing neutrino detectors near reactors, scientists can monitor their fuel composition remotely, as different nuclear isotopes emit antineutrinos with distinct energy signatures. It's like having an X-ray machine that works through concrete walls, no need for inspections when the particles themselves betray whether a reactor is producing energy or weapons-grade plutonium. The medical field is also tapping into neutrino tech in ways that sound straight out of science fiction. When a massive star collapses into a supernova, the first warning sign isn't the spectacular light show, it's a pulse of neutrinos that races ahead of the explosion. Networks of detectors like SNEWS, the Supernova Early Warning System, are already online, waiting to catch these cosmic distress signals. If a star in our galactic neighborhood goes supernova, the neutrino alert could give astronomers precious minutes to point telescopes before the visible fireworks begin. But the implications go beyond astronomy. Supernova neutrinos carry clues about extreme nuclear physics that could revolutionize our understanding of radioactive decay, potentially leading to breakthroughs in radiation therapy for cancer. Perhaps the most mind-bending application lies in communication. Traditional radio waves struggle to penetrate water or rock, but neutrinos laugh at such obstacles. Researchers have already demonstrated neutrino-based messaging through solid Earth, encoding data in particle beams that travel straight through the planet. Imagine submarines receiving commands from halfway across the world without surfacing, or emergency signals reaching miners trapped deep underground. The tech is still in its infancy. Current neutrino text messages take hours to send a single word, but the principle is proven. In a world where solar flares can knock out global communications, neutrino networks might one day serve as an indestructible backup. Yet for all their promise, neutrino technologies face hurdles as daunting as the particles themselves. Detectors must be monstrously large to catch even a handful of interactions, making widespread deployment impractical. False signals from cosmic rays or natural radioactivity can muddy the data, requiring layers of shielding and complex filtering algorithms. And then there's the ultimate irony, the very property that makes neutrinos useful, their ability to ignore matter, also makes them maddeningly difficult to control. Unlike photons or electrons that can be focused and amplified, neutrinos stubbornly refuse to be tamed, forcing engineers to work with the faintest whispers of signals. The challenges don't stop at engineering. Neutrino science thrives on international collaboration. Projects like IceCube and Hyper-K involve dozens of countries, but geopolitical tensions constrain these delicate partnerships. When a detector in one nation monitors reactors in another, questions about data sovereignty and trust inevitably arise. Even the dream of neutrino communication raises security concerns. A particle beam that can message a submarine could theoretically track it too. Balancing innovation with ethics and safety will be as crucial as solving the technical puzzles. What makes these efforts worthwhile is the sheer breadth of possibility. Neutrinos started as a theoretical band-aid to save the conservation of energy. Now they're reshaping fields from geology to cybersecurity. As detectors grow more sensitive and algorithms smarter, we're not just chasing ghosts. We're learning to harness the universe's most aloof particles as allies, turning their indifference into an unexpected superpower. The road ahead is long, but every hurdle cleared brings us closer to a world where neutrino vision isn't science fiction, but everyday science. Catching neutrinos is like trying to photograph a snowflake in a blizzard with a camera that only works once every 100 years. These particles interact so rarely that detectors must be built on a scale that borders on the absurd. Think tanks of liquid larger than office buildings, buried deep underground, just to catch a handful of meaningful collisions. The challenge isn't just size, it's purity. Even a whisper of contamination, a stray atom of uranium in the water, a cosmic ray slipping past the shielding, can drown out the delicate signals physicists are hunting. To build a neutrino detector is to wage war against the universe's noise, armed with nothing but ingenuity and patience. Take the liquid scintillators used in experiments like Camland or Juno. These cocktails of organic chemicals must be so pristine that even a single grain of salt dissolved in an Olympic-sized swimming pool would ruin them. Manufacturers purify the fluids in conditions rivaling semiconductor cleanrooms, filtering out natural radioactivity until the material is nearly inert. Then there's the shielding layers of lead, copper, and water, sometimes wrapped in ancient Roman lead salvaged from sunken ships, prized for its lack of modern radioactive contaminants. The goal isn't just to block interference, it's to create a silence so profound that when a neutrino finally speaks, its voice is unmistakable. But purity alone isn't enough. Neutrino detectors must also be vast because the particles are so evasive. IceCube transforms a cubic kilometer of Antarctic ice into a sensor, while Super-Kamiokande and 50,000-ton water tank is just the precursor to Hyper-K's 260,000-ton behemoth. Scaling up isn't optional, it's the only way to compensate for neutrinos' refusal to interact. Even then, success isn't guaranteed. When Japan's T2K experiment fires neutrinos 295 kilometers underground to the Super-K detector, only about 1 in a million arrives with a detectable collision. The rest pass through Earth like it's not even there. The data deluge from these detectors presents another hurdle. Modern neutrino observatories generate petabytes of raw information, most of it background noise. Sorting real neutrino interactions from false alarms requires AI systems trained to spot patterns no human could discern. At IceCube, machine learning algorithms sift through millions of cosmic ray events daily to find the handful that might betray a high-energy neutrino's passage. It's a cosmic needle in a haystack problem, where the haystack spans the universe and the needles are invisible. Yet for all these challenges, the payoff is worth the struggle. Neutrino research isn't just about satisfying scientific curiosity. It's a testing ground for technologies that ripple across society. The ultra-pure materials developed for detectors now purify medical isotopes for cancer treatments. The AI tools honed to analyze neutrino data are revolutionizing fields from weather prediction to financial modeling. Even the cryogenic systems keeping liquid argon detectors at -186 degrees Celsius are advancing sustainable cooling tech. When we push the boundaries of fundamental physics, we don't just learn about neutrinos, we invent new ways to solve problems here on Earth. And that's before considering the bigger picture. Neutrinos are cosmic witnesses carrying untouched information from the universe's most violent events. By mastering their detection, we're building the foundation for a new kind of astronomy, one that sees through dust, gas, and time itself. The same technologies that catch these ghostly particles today might tomorrow warn us of nearby supernova, monitor clandestine nuclear activity, or even open channels for communication that no firewall can block. The challenges are immense, but so is the promise. In chasing the universe's most elusive particles, we're learning to read its deepest secrets. Neutrinos might seem like the ultimate academic abstraction particles, so elusive they defy detection, studied in labs buried deep underground or encased in polar ice. But the quest to understand them is far from just an intellectual exercise. These ghostly particles could hold the key to technological revolutions that reshape our world, from clean energy breakthroughs to unhackable quantum networks. Consider nuclear fusion, the long-promised dream of limitless carbon-free power. While researchers struggle to contain star-like plasmas here on Earth, neutrinos offer a backstage pass to the sun's fusion furnace. By analyzing solar neutrinos, we've already verified that stars burn hydrogen through quantum tunneling, a process we're now trying to replicate in fusion reactors like ITER. The more we learn about how neutrinos carry energy away from these reactions, the better we can optimize our own attempts to harness star power. Then there's the materials science angle. Neutrinos interact so rarely with matter that studying them pushes detector technologies to their limits, sparking innovations in ultra-pure crystals and superconductors. The same hypersensitive photodetectors developed for experiments like Super-Kamiokande and are now being adapted for early cancer detection, spotting tumors at stages traditional imaging can't. Even the cryogenic systems keeping liquid argon detectors at near absolute zero are advancing medical MRI technology, making high-resolution scans more accessible. Perhaps the most transformative potential lies in quantum computing. Neutrino oscillations are essentially quantum processes writ large particles existing in multiple states simultaneously until measured. By deciphering these quantum dances, we're uncovering principles that could lead to error-resistant qubits, the building blocks of quantum computers. Some theorists even speculate that neutrino-like particles might form the basis of topological quantum computing, where information is stored in nearly indestructible quantum states. It's as if the universe handed us a blueprint for next-gen computing in the most unexpected package. Beyond practical applications, neutrinos are reshaping how we approach fundamental science itself. The discovery that these particles have mass, a finding that upended the standard model, taught physicists a humbling lesson. Sometimes the biggest breakthroughs come from chasing anomalies rather than confirming expectations. This mindset now permeates fields from materials science to medicine, where researchers actively seek out neutrino moments, seemingly small inconsistencies that could point to paradigm shifts. So when we ask why neutrinos matter beyond satisfying scientific curiosity, the answer isn't just about the particles themselves. It's about how pursuing the most obscure questions forces us to invent new tools, challenge old assumptions, and stumble upon solutions to problems we didn't even know we had. From the quantum realm to the cosmic web, these phantom particles are quietly guiding us toward a future we're only beginning to imagine. So where does this leave the mystery of the missing neutrinos? The answer, as we've uncovered, isn't that they vanished, it's that they've been masquerading as something else all along. Neutrino oscillation, that quantum sleight of hand where these particles switch flavors mid-flight, cracked the decades-old solar neutrino problem wide open. The neutrinos streaming from the sun weren't disappearing. They were simply changing costumes, morphing into types our early detectors couldn't see. This revelation didn't just fill a gap in our stellar models, it shattered expectations, proving that neutrinos have mass, a discovery that forced physicists to rewrite the Standard Model's rulebook. But the plot thickens when we peer beyond the textbook answers. While oscillation explains the solar neutrino deficit, anomalies in reactor and accelerator experiments suggest there's more to the story. Some measurements still show slight but stubborn discrepancies, as if a fraction of neutrinos are slipping through the cracks of our current theories. Could there be a fourth, even more elusive neutrino flavor, a so-called sterile neutrino, that interacts only through gravity, making it nearly impossible to detect? Experiments like Mini Bueni at Fermilab have picked up tantalizing hints of these phantom particles, with data showing unexpected oscillation patterns that don't quite fit the three-flavor model. If sterile neutrinos exist, they could be the dark matter that's been hiding in plain sight, or a gateway to physics beyond our wildest theories. Then there's the lingering question of neutrino masses. We know they're absurdly small, but why? The Standard Model can't explain their featherweight existence, leading to wild speculations about extra dimensions, unseen particles, or even cosmic accidents in the early universe. Some theories propose that neutrinos get their mass from a completely different mechanism than other particles, perhaps involving heavy, right-handed neutrinos that briefly flickered into existence during the Big Bang before vanishing. Others suggest they might be Majorana particles entities that are their own antimatter, twins, a property that could explain why the universe didn't annihilate itself in a burst of pure energy. The deeper we dig, the clearer it becomes. Neutrinos aren't just solving puzzles, they're revealing how much we still don't know. From their potential role in matter's cosmic dominance to their whispers of hidden dimensions, these particles are more than cosmic curiosities. They're keys to the universe's best-kept secrets, and every anomaly in the data is another clue waiting to be decoded. The case of the missing neutrinos may have been cracked, but the trial is far from over, and the verdict could rewrite reality as we know it. What if everything we thought we knew about neutrinos was just the tip of the iceberg, or worse, completely wrong? In 2011, the physics world erupted when the Opera experiment in Italy clocked neutrinos arriving 60 nanoseconds faster than light should have allowed. Headlines screamed that Einstein's theory of relativity had been toppled, only for the team to later discover a loose fiber optic cable had skewed the results. But while that particular claim collapsed, the episode revealed something profound. Neutrinos are so strange, so resistant to conventional rules, that even fringe theories about them demand serious consideration. Take the idea of extra dimensions, a staple of string theory that suggests our universe might have hidden spatial layers curled up too small to see. Some physicists speculate that neutrinos could be slipping through these extra dimensions during their journeys, shortcutting across cosmic distances in ways that would appear to break light speed limits from our limited three-dimensional perspective. It's like watching an ant crawl across a crumpled piece of paper. What seems like a long path to us might be a quick hop if the ant could tunnel through the folds. While no concrete evidence supports this yet, the math doesn't rule it out, and neutrinos' penchant for defying expectations keeps the door open for wild possibilities. Then there's quantum tunneling, a phenomenon where particles bypass barriers by essentially teleporting, through them. Normally, this happens at microscopic scales, but what if neutrinos, already masters of ignoring matter, could tunnel across macroscopic distances? Some models suggest this might explain why they seem to arrive slightly earlier than expected in certain experiments, though the effect would be subtle enough to dance on the edge of detectability. The cultural impact of these theories is just as fascinating. Neutrinos have inspired everything from sci-fi plots to avant-garde art installations. Artist Arthur Ganson built a machine called Corey's Yellow Chair, where a tiny neutrino figure perpetually walks through a solid chair, embodying their ghostly nature. In literature, authors like Kim Stanley Robinson weave neutrino observatories into dystopian futures, while musicians have translated neutrino oscillation data into eerie, otherworldly soundscapes. There's something poetic about particles so elusive they blur the line between science and metaphor, becoming muses for creativity as much as subjects for equations. What ties these threads together is the sheer audacity of neutrino science. Whether probing the limits of relativity or sparking artistic expression, these particles remind us that the universe's deepest truths often lurk in the gaps between what we know and what we dare to imagine. And as detectors grow more precise, who's to say which wild theory might one day cross over from fiction to fact? After all, neutrinos have made fools of predictions before, and they're not done yet. Neutrinos have slipped through more than just lead and rock. They've tunneled straight into the heart of pop culture, becoming metaphors for everything we can't quite grasp. Take the neutrino bomb, a fictional doomsday device in the 1950s sci-fi classic The Day the Earth Stood Still. The film imagined these ghostly particles weaponized, capable of silencing all electricity on Earth, a plot that, while scientifically absurd, perfectly captures how neutrinos embody the mysterious and uncontrollable. Even Hollywood couldn't resist their allure. In 2012, a neutrino detector accidentally opens a portal to another dimension, blending real science with cosmic fantasy. But it's not just blockbusters. Neutrinos haunt literature like spectral muses. Author Jeanette Winterson wove them into gut symmetries, using their quantum ambiguity as a metaphor for human relationships, particles that pass through walls but leave no trace, much like love or memory. Poets, too, have latched onto their ethereal nature. Tracy K. Smith's Pulitzer-winning Life on Mars imagines neutrinos as cosmic nomads, threading through space like a needle through cloth, stitching together the universe's hidden seams. The metaphor works because neutrinos are the intangible made tangible. They're the universe's ghosts, the particles that refuse to play by the rules, and that's catnip for storytellers. In video games like Mass Effect, neutrino emissions betray hidden alien tech. In Star Trek, they're scannable proof of wormholes. Even comic books get in on the action. Marvel's Fantastic Four once faced a villain whose power source was, you guessed it, a neutrino beam. But here's the twist. While pop culture simplifies neutrinos for drama, real-world science invites you to join the hunt. Citizen science projects like Zooniverse's IceCube neutrino hunters let anyone sift through Antarctic detector data, flagging potential cosmic neutrino collisions. Apps like Neutrino Watch ping your phone when a supernova's neutrino pulse hits Earth, turning you into a human alert system. Universities even crowdfund neutrino research, like the UK's NOVA Neutrino experiment, where backers get their names etched on detector components. The line between science and storytelling blurs beautifully here. Neutrinos inspire not because they're easily understood, but because they're not. They're the perfect bridge between the known and the unknown, inviting both physicists and poets to chase their shadows. And with every new detection, whether in a lab or a lyric, we're reminded that the universe's quietest particles often spark the loudest imaginations. You don't need a PhD or a particle accelerator to join the hunt for neutrinos. just curiosity and an internet connection. Across the globe, physicists are teaming up with everyday people through citizen science projects, turning the search for these ghostly particles into a collaborative adventure. Take Zooniverse's IceCube Neutrino Hunters, where volunteers sift through real data from Antarctica's icy detector, flagging streaks of light that might betray a high-energy neutrino's passage. It's like cosmic bird watching, except instead of spotting rare eagles, you're hunting particles from black holes and supernovae, but the opportunities go beyond clicking through images. Platforms like Cosmo Quest offer training modules to help enthusiasts learn the ropes of particle identification, while coding initiatives like CERN Open Data Portal invite programmers to analyze neutrino collision data using the same tools as professional researchers. Even if you've never written a line of code, projects like Science Scribbler let you transcribe handwritten notes from historic experiments, digitizing decades of neutrino research for future breakthroughs. The impact is real. In 2018, amateur participants in the Supernova Early Warning System helped confirm a neutrino burst from a distant star collapse, a discovery that later made headlines. Teachers are bringing these projects into classrooms, with students as young as 12 contributing to papers published in peer-reviewed journals. One high schooler in Norway spotted an anomaly in neutrino oscillation data that later inspired a new line of inquiry at Fermilab. For those who prefer outreach to data crunching, organizations like Neutrino Watch recruit volunteers to host stargazing events or build DIY cosmic ray detectors from cheap materials like plastic scraps and photo tubes. There's even a thriving community of neutrino artists who transform detector data into music, sculptures, and interactive installations, blending science and creativity to make the invisible tangible. The beauty of these initiatives isn't just their accessibility, it's their humility. They acknowledge that solving the universe's biggest mysteries requires more than elite labs. It demands countless eyes, diverse perspectives, and the collective curiosity of people who might never meet but share a common goal. As one IceCube researcher put it, every time someone clicks maybe a neutrino on our platform, they're not just helping us, they're rewriting what it means to do science. So whether you're sketching neutrino interactions as art or debugging code for a detector upgrade, you're part of a story much bigger than any single experiment. The hunt for these cosmic phantoms has become a shared human endeavor, proving that sometimes the most profound discoveries begin with a simple question: what if I could help? Arthur MacDonald still remembers the exact moment the solar neutrino problem cracked wide open. Deep underground in Sudbury's nickel mine, his team had spent years staring at data from their heavy water detector, waiting for a sign. Then, one afternoon in 2001, the numbers clicked. It wasn't a single eureka moment, he admits, but a slow dawning, like realizing you've been hearing a symphony all wrong, and suddenly the notes rearrange themselves. The solution: neutrinos weren't missing, they'd been changing identities all along. His Nobel Prize-winning discovery confirmed what theorists had suspected. These particles oscillate between flavors mid-flight, solving a mystery that had haunted physics for 30 years. Half a world away, Takoki Kajita was chasing similar ghosts beneath Japan's mountains. Super-Kamiokande and his colossal water tank lined with light sensors caught atmospheric neutrinos behaving oddly, some vanishing as they passed through Earth. We thought it was a calibration error at first, he laughs, but the anomaly held. By proving neutrinos could morph between types, Kajita and MacDonald didn't just answer an old question, they exposed a gaping hole in the standard model. Neutrinos had mass, and physics would never be the same. What drives these researchers isn't just the thrill of discovery, it's the tantalizing unknowns still lurking in the data. McDonald's eyes light up discussing neutrinos, particles born from Earth's radioactive core that could reveal secrets about our planet's heat engine. Kajita dreams of catching neutrinos from a nearby supernova, an event that might rewrite stellar physics in real time. Both share a quiet awe for how these minuscule particles connect scales from the quantum realm to galactic voids. When you hold a detector component, says MacDonald, you're holding a piece of a machine that listens to the universe's whispers. The human side of this quest is as gripping as the science. Kajita recalls sleepless nights during Super-K's construction, troubleshooting leaks in the massive water tank. MacDonald describes Sudbury's eerie quiet, 2 kilometers underground, where the only sounds are pumps and the occasional creak of rock. These aren't sterile lab stories, they're tales of perseverance, of teams working in darkness to illuminate the cosmos' deepest riddles. What unites them is a shared conviction: neutrinos are far more than cosmic oddities. They're Rosetta Stones carrying messages from supernova, black holes, and the Big Bang's afterglow. Every anomaly in our data, Kajita insists, is a potential doorway. MacDonald nods, adding, "We're like kids with a new telescope, except the universe handed us the wrong manual, and that's the fun part." Their passion isn't just for answers, but for the questions we haven't even thought to ask yet. As their tools grow sharper, Super-Kamiokande and successor will be 20 times more sensitive. They're chasing bigger game: sterile neutrinos, CP violation, even hints of quantum gravity. The best discoveries, MacDonald muses, are the ones that humble us. Kajita agrees, recalling how neutrino oscillation upended decades of certainty. Physics isn't about being right, it's about being less wrong, one ghost particle at a time. Their stories remind us that science isn't a solo endeavor. It's a chorus of curiosity spanning continents and generations, all tuned to the faintest signals from the dark. And as long as neutrinos keep surprising us, that chorus will keep singing, one detector, one eureka moment, one shared dream at a time. Wolfgang Pauli would likely be stunned to see how his desperate remedy, a theoretical particle proposed in 1930 to save the conservation of energy, has reshaped modern physics. What began as a mathematical band-aid has become one of science's most profound detective stories, with neutrinos at the center of not one, but multiple Nobel Prizes. The first came in 1995, when Frederick Riones and Clyde Cowan were honored for proving these ghostly particles actually existed, a feat many had dismissed as impossible. Then, in 2002, Raymond Davis Jr. and Masatoshi Koshiba won for their pioneering solar neutrino detectors, which exposed the glaring discrepancy between theory and observation. But the real earthquake hit in 2015, when Takaaki Kajita and Arthur MacDonald shared the prize for proving neutrinos oscillate, irrevocably shattering the Standard Model's prediction that they should be massless. These breakthroughs didn't just fill gaps in textbooks, they tore holes in them. Neutrino oscillation forced physicists to confront an uncomfortable truth: the Standard Model, their crowning achievement, was incomplete. Suddenly, particles once considered minor players became central to some of physics' biggest questions. Take the matter-antimatter asymmetry problem: why our universe is made of stuff rather than nothing. Neutrinos, with their ability to potentially violate CP symmetry, emerged as prime suspects in this cosmic whodunit. Their tiny masses also hinted at new physics beyond the Higgs mechanism, suggesting exotic particles or even extra dimensions might be lurking just out of reach. The cultural ripple effect is just as striking. Neutrino research has birthed entire subfields, from neutrino astronomy, where detectors like IceCube pinpoint cosmic cataclysms by their neutrino emissions, to Neutrino Studies that peer into Earth's radioactive heart. The technology spun off from these pursuits is equally transformative. Ultra-pure liquid scintillators developed for neutrino detectors now purify medical isotopes, while the same photomultiplier tubes that catch Cherenkov radiation in Super-Kamiokande and are being adapted for early cancer detection. Even quantum computing owes a debt to neutrino research, as their oscillations provide real-world examples of quantum superposition at macroscopic scales. What makes this legacy so extraordinary is its unpredictability. Pauli never imagined his particle that couldn't be detected would one day help explain why galaxies exist, or that chasing solar neutrinos would reveal flaws in stellar physics. The teams building early detectors didn't anticipate their work would pioneer techniques for monitoring nuclear nonproliferation. This is the neutrino's greatest gift. By being so stubbornly elusive, they've pushed science to invent new ways of seeing, not just for particle physics, but for medicine, planetary science, and beyond. Now, as Super-Kamiokande and Dune prepare to hunt for CP violation and sterile neutrinos, we're standing on the threshold of another revolution. The questions have grown bolder. Could neutrinos explain dark matter? Are they portals to hidden dimensions? Each answer promises to rewrite our cosmic story, proving that sometimes the smallest things cast the longest shadows. The mysteries neutrinos have unveiled are just the beginning, like pulling a loose thread only to find it's attached to the entire fabric of reality. As we stand on the edge of discoveries that could redefine physics, the next frontier stretches far beyond these ghostly particles. Gravitational wave observatories like LIGO and neutrino detectors are joining forces, creating a new kind of cosmic detective team. Imagine catching the ripple of colliding black holes through space-time while simultaneously spotting neutrinos from the same event. A multi-messenger approach that could reveal secrets about extreme environments no telescope could ever penetrate. This synergy isn't science fiction, it's already happening. In 2017, when LIGO detected neutron stars merging, telescopes worldwide scrambled to find the light. Now, scientists are tuning neutrino detectors to listen for these cataclysms too, hoping to catch a particle whisper that might explain how heavy elements like gold are forged in stellar collisions. But the real game-changer could be quantum gravity, the holy grail of modern physics. Neutrinos, with their ethereal indifference to matter, might be ideal probes for spacetime's quantum foam, the hypothetical turbulent subatomic structure of reality. Some theories suggest that if spacetime is pixelated at the smallest scales, high-energy neutrinos traveling billions of light-years could subtly betray this graininess through tiny delays in their arrival times. Projects like IceCube and the future Pacific Ocean Neutrino Experiment are hunting for these anomalies, where a neutrino's journey might encode the first experimental evidence of quantum gravity. It's a long shot, but as physicist Freeman Dyson once said, looking for the impossible is the best way to discover the possible. Yet before we leap too far ahead, a sobering reality check. These ambitions demand detectors of almost unimaginable scale and sensitivity. The proposed cubic kilometer neutrino telescope aims to instrument an entire cubic kilometer of ocean water with sensors, while plans for a lunar neutrino observatory would use the moon's lack of atmosphere to catch ultra-high-energy particles unimpeded. The technical hurdles are staggering, from powering deep-sea arrays to shielding lunar equipment from cosmic rays. And then there's the data deluge. Future detectors could generate exabytes of information daily, requiring AI so advanced it might need to invent new physics just to sort the signals from noise. What makes this moment so electrifying isn't just the tools we're building, but the questions we're daring to ask. Could neutrinos help us crack supersymmetry, the theory that every known particle has a hidden twin? Might they expose hidden dimensions curled up like discarded origami at scales we've never probed? Every anomaly in neutrino data, like the persistent low-energy excess some detectors observe, could be a breadcrumb leading to realms beyond the standard model. The line between neutrino physics and metaphysics is blurring, and with it comes a thrilling possibility. The next Einstein might not be staring at equations on a chalkboard, but sifting through the faintest flashes in a tank of Antarctic ice, chasing shadows toward a revolution we can't yet imagine. Building the next generation of neutrino detectors isn't just a scientific challenge, it's a test of who gets to participate in unraveling the universe's secrets. Projects like Super-Kamiokande and Dune cost billions, requiring collaborations across dozens of countries and decades of sustained funding. But here's the uncomfortable truth. The nations and institutions footing the bill inevitably steer the research priorities, while entire regions with brilliant minds but limited resources watch from the sideline. This isn't just about fairness, it's about lost potential. Imagine the breakthroughs we might miss because the next Einstein or Marie Curie is studying under a kerosene lamp in a village without reliable electricity, their genius untapped by a system that equates funding with opportunity. The geography of neutrino research tells a stark story. Of the world's 15 major neutrino detectors, none reside in Africa or South America. Indigenous communities with ancient astronomical traditions, like the Polynesian navigators who read star paths or the Inca engineers who align temples with cosmic precision, rarely see their descendants represented in modern physics collaborations. Even within wealthy nations, participation skews toward elite institutions, leaving smaller colleges and historically marginalized groups scrambling for scraps of data. When the IceCube team published their landmark neutrino discovery in 2018, the author list spanned 12 countries, a step forward, yet still excluding vast swaths of humanity. But change is brewing. Initiatives like the African School of Fundamental Physics are nurturing homegrown talent, while programs in Chile and Brazil are fighting to place Southern Hemisphere detectors on the map. The key isn't charity, it's rethinking how knowledge gets shared. Open data policies, like those pioneered by CERN, allow researchers anywhere to analyze neutrino collisions without needing a billion-dollar lab. Citizen science projects democratize discovery, letting students in Nairobi or Lima help classify particle events from Antarctic ice. And when Japan's T2K neutrino beam collaboration expanded to include Thailand and Vietnam, it wasn't just about adding manpower, it was about incorporating new perspectives that spotted anomalies others might have dismissed. The stakes couldn't be higher. Neutrinos don't care about borders or budgets. They flood the globe equally, offering insights into everything from earthquake prediction to clean energy. But if only a fraction of humanity has the tools to study them, we're effectively censoring the universe's messages. This isn't just inequity, it's intellectual starvation. The solutions aren't simple, but they start with acknowledging that curiosity isn't confined to wealthy nations, and innovation thrives when barriers fall. The next neutrino revolution might not come from a lab under Geneva or Chicago, but from a makeshift observatory in Jakarta or Lagos, where someone finally gets the chance to ask a question no one else thought to pose. As we peer deeper into the quantum shadows these particles cast, let's remember, the cosmos speaks to everyone. Our detectors should too. Neutrinos are more than just particles. They're cosmic storytellers, whispering secrets from the heart of stars, the wreckage of supernovae, and even the aftermath of the Big Bang itself. Think about that for a moment. Every second, trillions of these ghostly messengers pass through you, carrying tales from the most violent and wondrous corners of existence. They've taught us that the sun's core burns not through ordinary fire. but quantum tunneling, a process so delicate it defies classical physics. They've revealed that even the most established theories, like the Standard Model, are incomplete, waiting to be rewritten by the next curious mind. But here's the truly humbling part. Neutrinos don't just connect us to the universe, they connect us to each other. The global hunt for these particles has united scientists across continents, languages, and cultures, all chasing the same elusive truth. From the icy depths of Antarctica to abandoned mines turned into underground cathedrals of science, these collaborations remind us that discovery is a collective effort. When a detector in Japan catches a neutrino from a supernova, or a lab in Canada spots a neutrino born from Earth's molten heart, it's not just a win for physics, it's a triumph for human curiosity. And that's the real lesson neutrinos offer. The universe is far stranger, far richer than we ever imagined, but it's not indifferent to our questions. Every time we build a better detector, refine a theory, or even just gaze up at the night sky wondering, we're adding another verse to an ancient conversation between humanity and the cosmos. So keep looking up, stay stubbornly curious, because the next great discovery might not come from a particle accelerator or a supercomputer. It might start with you, a backyard telescope, and the quiet courage to ask, what if? The universe is listening, and if history's any guide, it's ready to